order to overcome that limitation, we wanted to come up with two different methodology. So one is fixing size of the bin, determining number of data instance falling in each bin. Number two is fixing the number of data points falling in each bin and determine the size of the bin. So let's start from here, kernel density estimation. So here we want to fix the size of the bin. So one of the common methodology, widely used methodology is Poisson window. So in this case, we want to estimate multiple bins. So for each data that we observed, for each data point, we want to apply a bin. Well, sort of. So this is informal. So what's happening here is we'll try to put a bin like this for every different instance that you observed from the data set. And at the end of the day, you count the number of bins that are accessible. So calculating P is simply counting the number of bins. So let's take a look at the derivation. So let's start from the probability quantity that we came up with. So that is Ki over NBI. Again, K is defined using this new function K. So this new function is 1 when this satisfies and 0 otherwise. Basically, this means, let me start over. So it should be, you want to estimate the probability from here. So in order to do that, what you want to do is putting a bin around it and count the number of instances in the bin. Unfortunately, there is no instances for this region. So here, X is just representing the point that I'm estimating the probability, where X1 and X2, these are actual data points. So if my data distributed in this way, Px is 0. But say, fortunately, if there is one additional data point, P around the X, so say here is X3, then I have a count. So where it's going to be, where K will give me 1, where sort of. So eventually, you're estimating this window, so this bin, over every different instances. So calculating K, that is counting the instances falling in each bin, is now switched to this function, K function. And this K function is indeed called as kernel. And this specific form of the kernel is called as Poisson window. So Ki is defined in this way. And now let's update the original function Px. So Ki is updated using this notation. So putting here. And we want to also update B. So B is changed H to the D. So it is representing a sort of dimensionality. At the same time, there is a shared variable H, where this is actually controlling the size of the bin. So since this is controlling the size of the bin, it has a name that is bandwidth. So let me restate stuff. So where we started from the estimator, we came up with from the histogram, and this kernel density estimation using Poisson window is updating this probability estimation using this form. This form has two important components in it. So instead of counting the data points falling in each bin, we are using a new function K. This is called as a kernel function. So using kernel function, where given a estimating point, you want to count the number of data around it. And this function is also updated in terms of BI. So BI becomes HD. So HD is representing the size of the bin or size of the kernel. And this is not coincidence, but where we are looking H in two different places. Actually, that is controlling the size of R, or size of the bin. So for this region, this is called as bandwidth. So this is similar to the bin size that we have seen. So bin size is small, then it is a higher resolution. Bin size is big, it is smaller resolution. So bandwidth is high, it is smoothed more. When bandwidth is low, it's smoothed less. So, well, let's take a look at this example. So, well, I actually felt some kind of disconnection in the middle of my description, so I would like to move on to this example. So, well, here the example is saying bandwidth is 4, and we have 10 samples. Out of this, we want to estimate the probability at 3 different places, 3, 9, and 15. So let's try to consider the case of P3. So using kernel density estimation, what you do is putting kernels. So you are putting kernels for each data point. And bandwidth is 4. So for the first data point, you're putting a kernel like this. So size is 4, and you're putting the kernel around your data object. And next one, something like this. And next one, something like this, or something like this. So you are putting kernels around each data observation. So here is your data point. This is the actual region of the kernel, or something like this. But given that, we try to visualize all the kernels that are applied to each of our 10 samples, and the bandwidth is 4. So each data point is centered, and each kernel is located somewhere like this. But given that, let's try to estimate P3. Well, what you do is simply counting the kernel that is overlapping with region P3, X3. So if you look at this area, well, there is only one kernel overlapped. So what this calculation is representing, you first want to multiply n, which is 10. And this is your bandwidth. And we are looking at one-dimensional data. So this is 4 to the 1. And we have one kernel is overlapping with this point. So that is 1. Other than that, all the other kernels, they are not overlapping. So you are simply putting zeros. And if you calculate this multiplication, then you can easily get 0.025. Now let's think about P9, where this specific point, it does not overlapping with any of the kernel. So where we start with writing down n and h to the d, which is 4 to the 1. And none of the kernels are overlapping with 9. So this is probability 0. And now let's consider px equal 15. So n 4 to the 1. And there are actually multiple kernels overlapping. So maybe this guy, this guy, this guy, and this guy, and even this guy, right? Oh no, so this is enough, where you have 5 data points whose kernels are overlapping with x15. So you are adding all of them as 1. So eventually it's going to be 5 over 50, 5 over 40, so 0.125. I hope you get the idea. So, well, it is completely the opposite of calculating the histogram. So histogram, you're putting bin, and that is fixed, and you're trying to fit the data to the bins. But here, we are putting corners on each of the data observed. And when you want to estimate the probability at certain point, we want to count the number of corners that is overlapping with my region. So that is Parjan window. Corner density estimation is the Parjan window. And there is one extended version of corner density estimation. So where this Parjan window is simply just uniform across the space. And maybe we can smooth this using a Gaussian-like shape. So it is actually following the shape of the Gaussian. So corner is defined in this way. We may be able to describe the density in more smoothed form, and open cases, this is somewhat more preferred. So if you use corner in this shape instead of this simple indication, when you estimate a probability at certain point, you are getting corner calculated from this RBF form, so Gaussian form. And this diagram is showing the distribution of the corners. So you are calculating the corner on each data observed. So for this, you have this quantity calculated. For this second data point, you have this quantity calculated. So it is similar to Brajan window, but smoothed and shaped like bell curve. And eventually, when you estimate the probability at certain point, like here, so adding up all the blue values, and you ended up having this red value. So that is the idea behind the KDE with the smooth corner. And like we discussed, the bandwidth is something similar to the smoothing factor that we have seen in the histogram case. So when bandwidth is getting larger, then it's going to be smoothed more. So in case of H10, where maybe it is too smoothed or too dull. When KH is 1, where you are looking at the data at the highest resolution, that means where some of these estimation would be very sensitive what you are observing from the data space. So it is more picky and it is narrower. As you increase the value h, where things are wider and smoother like this. So where this is where sort of everything about KDE. So we looked at the formula P, K, and B. And from here, n is fixed, and we want to fix size of the corner or form of the corner in certain way. And eventually, we want to determine K in different way compared to histogram. Now let's move on to K and N. So in this case, we want to fix K, and we want to determine B. So where many of you have at least heard of K nearest neighbor at least one time, but now you can think of the same methodology in this way. We want to estimate the size of the region based on the number of data instances. So where maybe this is the circle that is encapsulating the neighborhood, where K is 3, where this dashed line is visualizing the region or bin that is containing this much of population. So we want to fix this number of neighbor first, and later on we want to determine the size of a region or bin. So if you do so, you can calculate and visualize the distribution in this way. So where this is the area of the K3, this is the area K4, K5, and this is K9. Where maybe you can come up with some kind of contour like this eventually. So you can estimate the distribution using KNN method, and eventually what you get is very similar to the true distribution, true data distribution. So that is what this example is showing. So, well, from this slide, I simply would like to show you how to teach your thought. So maybe many of you have experienced KNN methodology and it's one chance. Well, even if you haven't seen KNN methodology, well, understanding the methodology is very easy. So we want to look at the neighborhood and make a decision. But before you make any decision, well, KNN is also an estimator for density. And the density estimator, KNN density estimator, is working by first deciding number of neighbors. So K is 3, this is the size of bin. K is 5, this is the size of the bin, and so on. So determining size of the bin is equivalent to determining density. So where we looked at two different non-parametric density estimation method. One is kernel density estimation, where I hope the main idea is carried over to you clearly. And then we moved on to KNN density estimator. We often ask how to use kernel density estimator in midterm exam or homework problem, things like that. So I'm preparing some related problem for homework, next homework assignment. So well, let's try to exercise more with those problems. In the meantime, well, here is a quick comparison between parametric method and non-parametric method. So parametric method, once the model is fitted, only the parameter is need to be stored. So, well, this is something we discussed earlier. You have data, so this guy is x1 to xn, so you have so much of data, so you need some space in your storage. But from here, you assumed Gaussian distribution, and you estimated parameter mu and parameter sigma square. Well, once you have done it, you just need to memorize mu and sigma square, and that's it. You don't need to keep data. So, well, that's the advantage of a parametric method. Well, compared to parametric method, well, let's think about the same aspect for non-parametric method. So, in the previous case, in order to calculate P3, you actually need to go back to every single data point and estimate if kernel is ranging and overlapping with my estimating point, right? So in order to estimate any probability quantity, you need to keep all the data points. So that is described over here. So non-parametric method, you need to maintain all the data set while you are estimating probability. So that is maybe drawback. Also, we're estimating MLE is more efficient compared to estimating all different kernels on every single data observed, especially if you consider the smoothed kernel that is Gaussian on every single data point. It's expensive in terms of computation. But there is a big benefit. So non-parametric method, they are definitely flexible. So we did not assume anything about the underlying data density distribution. So maybe we can easily model a distribution with 2 peaks or multiple peaks. So if your data distributed in this way, non-parametric method would be preferred choice. Where if your data distributed more like canonical form or more like conventional form, then you can choose parametric because it is more efficient.